Welcome back. This is College Algebra 1.2, Functions and Graphs. This is part 2. We're going to talk a little bit about functional notation. And I know I've already addressed this a little bit, but I want to make sure that we are real specific. That f of x, like this, means the function that depends upon x. And we shorten that up, because mathematicians, of course, have to shorten everything up, to f of x. Okay, this is exactly the same as what we normally think of as y. This is our output. This is the function that is depending upon whatever the input was. So the advantage, though, of this notation is that when you write it, you have, for instance, you know when you have f of 3, it tells you that the x value is 3. So if you had a situation here where you're given y equals 7 times 5, you're not necessarily going to know whether the 5 or the 7 is the input. Where if you have, oh, sorry about that, I gotta get my pen. If I have f of x equals, say I have 7x, that means I'm going to have f of x, where my x is 5, is going to be that 7 times 5. So it's a notational thing. It helps us out a little bit. That information, if it's not instantly available, if you would have to kind of work through and figure out what it is, comparing some of your outputs to what is happening with your inputs, it could be a little bit of work that you wouldn't have to work on otherwise. All right, so I'm going to talk about graphs of functions, and I want to be real clear that every single line ever, with one exception, is a function. So the one exception is when you have a vertical line. There are infinitely many solutions, and there are not every input is going to have an output. So you have infinitely many solutions for one x. So that means this cannot be a function. You've got infinitely many, and you've got a whole bunch of outputs or inputs that don't have outputs. Okay, so that kind of breaks whether or not it's going to be a function or a relation. All right, so this one for sure is going to be a function, right? I have a point, a single point, for every single x value. I have an output, right? We don't know necessarily what it is, but the shape of the graph tells us for sure that we have a function. If you take a look here, again, we don't have any places that overlap, right? It wiggles, but there's no place where you have more than one solution. So this is also a function. All right. Here, this is not a function. All right, and I'm going to change this to red so it's maybe a little easier to see. If I were to take a look here, you can take a look at this x. I have one solution here, and I have another solution here. The second you have a second solution, you don't need to keep looking at all. You're done. You know that this is not a function. This is only a relation. Now, this is an interesting case. Here, I'm going to say, if I'm talking about, let me do a better job at that. If I'm talking about the inputs that go from, where are we at? Okay, there I am. If we're talking about the inputs that go from here to here, right? This is going to be that domain. This is our domain, our inputs, right? This is our domain. As long as this is our domain exclusively, we can take a look and see whether this is a relation or a function. So in this case, because I can cross this twice, assuming that this was a straight line, if I can cross this thing twice, I know that I have a relation, not a function. Right? If I have more than one solution anywhere on my inputs, then I have a relation. Now, here's the catch. If we take a look, and I'm going to use a big dark blue here. If we take a look and say this is the domain, oops, right? If we say this whole thing is the domain, do I have inputs here? I have inputs that don't have an output, right? So this is no f of x, right? There's no value there. So it would be neither. It's not a function and it's not a relation, right? And again, I have something here. There's no solution here and there's no solutions here. So there's no f of x. And in that case, we would say that it's neither a function or a relation. Remember, you have to have, for each input, you have to have at least one solution for a relation. And you have to have more, or you have exactly one if you want it to be a function. Okay, so let's go ahead. Here's a couple more. This case, right, I'm going to go ahead and take a peek here. Let's go ahead. This is going to be a function, right? Nowhere in here is there a place where I can draw a vertical line, and we're going to talk about why we would do that. There's no place here where we would be able to draw a line and hit the line a second time. Okay, so we can't, there's no second value for any of my x's, right? There's only one solution for each of my x's. Now, if we take a look here I'm fine, right? Here I'm fine, and then all of a sudden, if I drop this, well, not quite that. If I were to drop a line, sorry, trying to make this quick and I'm not doing a very good job of it. So if I were to take and draw a line here, right? We'll pretend that's a vertical line. You can see that I have at least two solutions, right? Here I've got my two solutions. And if I were to drop something here, now I've got three solutions to this particular x value. So here we have a relation. We don't have any places that don't have, for our x, we don't have any locations that don't have an f of x. So this is definitely a relation. Now you can take a look and see what I've been doing, and the reason we do it is it makes it really easy to see whether or not we have one solution for each input or whether we have two or more solutions. Remember, if we have two or more solutions, we're talking strictly a relation, right? We don't have an a function as well, right? So here you can see I have all of these different lines. It's a vertical line. If I drop a vertical line anywhere along any of these x values, I'm only going to cross this thing once. Again, that is, by definition, we have a function, right? We have a function if our I'm going to use a fancy schmancy information. So it says if and only if is this fancy double IFF, right? The double F's on that. It says the function, it is a function if and only if each x has exactly one f of x, right? That's the definition of a function. So in this case, it is a function, right? It wouldn't matter anywhere that I drop a vertical line. It's going to be just fine. Here, if I were to look here, I could, you know, if I only dropped it once, I could say, oh, well, this is probably a function. But the second I drop that next line, that next vertical line, I can cross it twice. And so I know it is no longer a function. It could be a relation. And I'm going to assume that I'm dealing with my domain being this, right? So here's my domain. I'm not going to get into the whole, it's neither again, but I wanted you to understand. So if I have a domain here that's this is a relation. All right. Again, here I have my domain is all real numbers, right? But if you take a look, here I have one solution, right? No matter where I drop this vertical line. My range, which is really a remarkable thing, my range on this is -4. There is no other place that there's a solution, so my range is literally just one number. Okay, here I might say that my range is between here and here, right? This would be my range. If I can write this as a not the best sideways writing I've ever done, but there we go. So this would be the range, and so everything beyond those points would not be included anymore if we're going to mark our domain and our range. But I wanted to make sure that we're real clear here that you can have a range that is exactly one number. Okay, I'm going to go ahead and leave those blank. I'm not going to worry about that. Here I want to talk about whether or not we have access to every single point. And it's possible that we won't, right? Here we have a function that if I plug in my f at 1, I'm looking for my function at 1, I'm going to have 1 over 1 minus 3, right? So this is my f of 1. Here I have -2, right? When I subtract this, I'm going to have a -2. So this is my solution right here. It's going to be a -1/2. That's allowed. That's fine. There's no reason I would have to exclude a number there. Now, if I go with f at 3, or f of 3, I'm going to have 1 over 3 minus 3, which means I have 1 over 0. And remember, we cannot do any kind of division with 0. All right? So my solution, what is my domain? My domain is going to be all real numbers where except we're going to say x cannot equal 3. Okay? If we wanted to write it in set notation, we could say we have the x such that x is a member of the real numbers and x is not equal to 3. Oops. There's my 3. All right. And there's my bracket. So that would be how I would say that domain in set notation. All right. So here, excuse me, here we're being asked to see if these numbers would work in the domain of the function. So I'm going to take a look at each one of these. I've got 3 different numbers. So the first one, I'm going to have my f of 16 is going to equal the square root of 16 plus 5. And this works. This is allowed. Now, because this is a perfect square under the square root, I can take it one step further. I can have a 4 plus 5, which is going to get me a 9. Okay, so far so good. Here, I'm going to have an f of negative 7, which means I'm going to have a negative 7 under the square root. Now, some folks know that this is going to give you an imaginary number. Generally speaking, at this point, we would talk about the fact that there's no real solutions. Okay? So, no real solutions. For the moment. We will get into complex numbers and deal with imaginary numbers at some point in the near future, but for the time being, we're going to go with the fact that there's no real solutions. Now, I want to point out here, if I have f of 7, I have the square root of 7 plus 5. That's actually allowed. Now, normally we would have our 5 come first. All right, so 5 plus the square root of 7. The square root of 7 is going to be not an imaginary number, but an irrational number. Irrational numbers are real numbers. Remember our tree rings there. So an irrational number is still going to be a real number, so that is our solution. We have a solution right here. Okay? Let's take a look. I think, yep, one little bit more. All right, so here I'm looking at the domain, and I'm saying that x, we have x as the domain such that x is going to equal negative 9 and then negative 8 and so on up until we get to 0. So we're not there's no spaces in between, or there's no line connecting in between here. I just have those exact dots. Okay, so my domain here is going to be the negative 9 on up. My range is going to be similarly, right? This is going to be 2, 3, 4, right? 2, 3, 4, 5, 6, and so on until we get to 11. All right? In this case, again, there's nothing connecting them, so we have to take the exact value, right? In this case, over here, right? If I'm going to assume that my domain is here, right? In between these 2 points, I have the domain is going to be all real numbers between negative 12, right? Because this is my negative 12, and 1 inclusive. So this is, if I were to like draw the picture, I would probably put dots on there, or put a square bracket in case I wanted to make sure that people understood that that's included. So my real numbers between negative 1 and, or negative 12 and 1 inclusive. In this case, my range, right, my range starts, the top value is going to be 1. All right, and so I'm including everything in between, and I go down here and I'm at, like 5.5 at my lowest point right here. So negative 5.5 is going to be less than or equal to x, which is less than or equal to 1. All right, so that's our range. A couple things. We have applications involved in all sorts of situations where we're going to deal with almost every science deals with linear functions, and certainly functions, and businesses use linear functions a lot. here we have an example of the linear expansion of a bridge, how much the center span of a suspension bridge moves. It's 1,420 meters long, okay, and it changes a little bit depending on the temperature. So this is like 0.000013. So this is like tens, hundreds, thousands, 10,000s, 100,000s, and now we're talking into millions. So 13 1/millionths. It's going to move, and it's going to be increasing for each meter by that temperature. So if our temperature is 0, of course this goes to 0. If this number is 10, and I don't remember that they recall, I'm going to just assume that since they're talking about meters, I'm going to assume that we're going Celsius degrees. I don't know that that's true, but for the moment we're just going to take that. So if our 10 was our Celsius value, right, all of a sudden this is going to go, it'll be 10 times, this will move over 1. So this becomes the 13 100,000ths times the 1420, okay? And so that would move our variable, or move our decimal over 1 this way, or move what we're thinking of in terms of this is 13 millionths. You would think of it as being 13 100,000ths. If you want to see a really interesting bridge, there's this bridge that was made out in Washington State, and it was worked. It was really well done, and then all of a sudden they had some serious wind storms come through, and it was really interesting. It actually collapses, and it didn't collapse, from the beginning. It collapsed as they went along. Also, you can have like projected sales, moving along here, projected sales for business. Here's an example of that. I'm going to let this go. I didn't realize I was quite this long. I want to make certain that this gets uploaded. All right.